In this video, we're going to talk about how to graph logarithmic functions. So previously we talked about how the logarithmic function is just the inverse function for an exponential. So in order to graph a log, we need to start with the graph of the exponential. So we're just going to go ahead and do this, the graph of f of x equal to the 3x power like we did in 3.1. So we're going to use these x values of -2, -1, 0, 1. And remember, those negative exponents are giving us fractions. And so the exponential curve is, remember, it's going to have that horizontal asymptote on the x-axis. But how are we going to use this to find the log function? Well, in this case, all we're going to do here, since, remember, for an inverse function, we find that by swapping the x and the y, what we're going to do here is we're actually going to just swap the coordinates of the exponential graph to find the log coordinates. And so if we do that, I'm going to bring these over in this table here. So if we go ahead and swap these coordinates here, that means instead of -2, 1/9 for the exponential, we'll get 1/9, comma, -2 for the log graph. Same thing, 1/3, -1. And then the more important one, remember, the exponential function always had a y-intercept at 1. Well, if we swap those, then the point now becomes 1, 0, which would be an x-intercept. So a log graph will always have the x-intercept of 1, 0. If we go ahead and look at these then, this is the same thing as saying, well, 3 to the y power equals x. So instead of plugging in values for the x's, we're actually plugging them in for the y's. It's just rewriting like we learned how to do that last lesson. So instead of log base 3 of x, it's the same thing as saying, well, 3 to the y power equals x. So 3 to the 0 power is 1, 3 to the first power is 3, 3 to the -1 power is 1/3, and 3 to the -2 power is that 1/9. We're swapping those guys. So from here, let's go ahead and graph both of our functions, the 3 to the x power, the exponential, and log base 3 of x, the logarithmic, in the same rectangular coordinate system, so the same coordinate plane. I went ahead and recopied over the coordinates for our exponential, but then I want to rewrite our exponential for our log. I want to rewrite the logarithmic here as an exponential. So instead of log base 3 of x equal to y, I'm going to rewrite that as 3 to the y power equals x. So in this case, we're going to copy down those y values in the y column, and then go ahead and switch those guys over there. That last point should actually say 9 too, so I made a mistake there. So if we go ahead and graph these points on our graph, we're going to get that exponential curve that we're used to with that horizontal asymptote on the x-axis. But if we plot our red graph, our logarithmic function, we actually see that to the right, we're going off towards infinity, growing very slowly, not quite as much as the exponential was, but more importantly, as we're going to the left, are going from 1 to 0 on the x-axis, our values are getting more and more negative. It's actually going more down towards that negative infinity as we get close to 0. So this means we're actually, instead of having that horizontal asymptote, we're going to have that vertical asymptote at the y-axis. Another way that we can check that we graph this correctly, remember that if we have inverse functions, they have to have that symmetry over the line y equal to x. And notice if I were to fold that blue graph over that line, it would match up perfectly with the red graph, proving that these are actually inverse functions. So let's go ahead and talk about some characteristics of the logarithmic function in the form where we have log base b of x. So it's going to be for any base. Remember, since the exponential and the logarithmic are inverses of each other, that means the domain and range for those guys are going to be swapped. So the domain here for the log base b of x function will be that 0 to infinity. So you can think about wherever that, from the y-axis all the way to the right, because we saw that vertical asymptote. The range, on the other hand, goes all the way down and all the way up on the y-axis, so we get all real numbers. Similarly, just like the exponential had a y-intercept at 1 every time, well, this means that for the opposite there, we're going to get the log function to have an x-intercept at 1, at 1, 0. And since we have that vertical asymptote on the y-axis, This means we have no y-intercept. Another fun part is that just like the base had played a big part in the exponential function, it's the same thing here with the logarithmic function. If the base is greater than 1, then this is going to be increasing to the right as an increasing function. So we'll start at that y-axis going all the way from -infinity and keep growing to the right. But if it is going to be a fraction where b is between 0 and 1, the graph is going to still go to the right, but in this case it's going to start going down. So it's going to be starting up by the y-axis and then going down towards the right, making this a decreasing function. And kind of like what we already mentioned here, even though that the logarithmic graph is going to have a vertical asymptote on that y-axis. One of the most common types of logs that we use is what's called the common logarithmic function, and this is when the base of the logarithm is 10, just because our number system is based on 10. So think about number place. We go from ones to tens to 1,000, and the other way we go tenths, hundreds, thousands, millions. So if we ever see a function where just written log x, it's automatically assumed to be base 10. These are going to be interchangeable. They're equal with each other. So let's try this here. It says here that the percentage of adult height attained by a boy who is x years old can be modeled by the function 29 plus 48.8 times log of x plus 1. Notice it doesn't give us a base, so this is going to be base 10. So this is where x represents the boy's age and f of x represents the percentage of his adult height. If we want to know what percentage the boy will have at age 10, then that means we need to plug in 10 for x. So if we go ahead and set up our function here, we'll get that 29 plus 48.8 times log of 10 plus 1. And if we go ahead and simplify that, remember that log there is base 10, so it's our common log. And go ahead and simplify that, we're going to get log of 11, which is all going to come out to about 80%. So a boy by age 10 has attained about 80% of his adult height. Some of our properties of common logs. So all the logs properties that we talked about before also apply to common logs. Just remember that if it's not given a base, it's going to be base 10. Another common log that we talked about was the natural log. And this is going to be a logarithm with base e. So just like e was the natural exponential, its inverse is what's called the natural log. And we abbreviate this as ln. So log base e of x is going to be equal to that ln of x. And these properties that we talked about before still hold for the base e. It might just be written a little bit differently, but that ln still applies to those logs. So here's an application of natural logs. It says when the outside air temperature is anywhere from 72 degrees to 96 degrees Fahrenheit, the temperature in an enclosed vehicle climbs by 43 degrees in the first hour. The function 13.4 times the natural log of x minus 11.6 models the temperature increase f of x in degrees Fahrenheit after x minutes. Use the function to find the temperature increase to the nearest degree after 30 minutes. Pause the video here and try this one on your own. We'll notice it says that to use the function after 30 minutes, that means we're going to plug in 30 for our x. So we're going to be finding f of 30 here. This means that we'll get 13.4 times the natural log of 30, notice the parentheses, minus 11.6. And so this is the case on our calculator where we want to use that ln button. So make sure you find that. This, again, the ln is going to be our natural log, which is base e. And so if we go ahead and simplify this, it turns out to be about 34 degrees, which is what we said would happen.